So once you're just talking about textiles, so the textile production is very old, very, very old, possibly older than, like pottery and even agriculture. So the anthropologists, they estimated humans began wearing clothing somewhere between 500,000 and 100,000 years ago. So the first assumption is, like the people thought, like, okay, people began wearing clothing or like spinning fibers from the local resources, which are either like flax or cotton-like structures. But even though among the fragments of remain, like say for textiles because they are biodegradable, one of the good examples they found is in a Neolithic site in Çatalhöyük in Turkey. And what the scientists discover is actually that our ancestors, they basically spun, like their clothes from the bark of oak trees. So they're not like quite soft structures, but I think it's also a very good reference how we use the natural resources around us. And this is how it begins. So at Royal Council, I'm part of a program which is called Design Futures, and I give soft robotics lecture with the textiles program. So we call this soft system. So it is an interface between the physical and digital world. Not about the, like the system, the electronic system that you design, but also how you put everything in together. So that's why we are quite keen to embrace a material-led approach rather than bringing all these components. And for us, the textiles is actually a system. There is a taxonomy from fibers, like starts from the nanoscale. So you design the polymers, you design the orientations, you control them, you control their either mechanical or any kind of macro properties. You spin them into fibers, like you construct clothes. So this could be like a knitting cloth, it could be like a woven structure, but eventually you turn this to something quite tangible that you can work with. So, and also, which is quite important for textiles, I had this conversation a lot with my colleagues who are like physicists. Is the textiles and fashion is just about aesthetics? So it's not just about aesthetics. So I think even the definition of aesthetics is a very good starting point. Is actually the aesthetic terms is about the perception of the object, is the sensory perception object. And that is quite linked with the, like the human acceptance and also the user acceptance. So whatever you design in your, like applied research, applied material research, in order to have like a take from the industry, it needs to respond to your senses, right? So if you just create something quite itchy or rough, even though it's quite functional, they're not gonna basically use in their, like final designs. So there is this, like this gap in this jumping, this Ferrari level also. So what I love about textiles is not just because I'm educated in textiles engineering, but also textiles differ in many ways. So it is okay to be crafted, that we call like the craft intelligence. There are some things, like, so they don't have to be automated all the time. So of course, in all this textile machinery, if you know it, it's like a weaving loom or a knitting loom, they're like quite fast. And they also, what we aim, like as an engineer, we also aim like to keep like the minimal defects ratio. That's right. So this is how we just basically educate it. But at the same time, just using the, like the textile methods, textile meeting methods, this could be quite simple, like stitching, like crochet, or like, I mean, this kind, even like simple printing that I'm going to show you some examples. It's okay to, like to stay in the like the love range of manufacturing, because it's also embed a different kind of creative practice, especially with the material science and especially with the nanotechnology, since we deal with like small quantities. That's the, like it's one of the textile tools itself. It also gives this opportunity to create something unique and then create something, like quite acceptable for others. So you can make your tools. And there is also, I think the beauty is there's a hierarchy in textiles. From the nanoscale, so it's about the finishing, it's about the, like the coating, but there's a hierarchy. And each hierarchy like even though you use the same materials, you can create something unique in terms of properties. So what they can promise, so textiles can promise complexity. You can create like multi-layer structures. It's quite, like common in composites, for instance. It's textiles, the most of the structural composite structures that you use, like the textiles itself as a reinforcement. That's one thing. And it's also can be quite simple, and there's nothing wrong about it. So your process can be slow or fast, but it's not going to affect the overall quality. So you can still get something quite delicate and exquisite, not just about the aesthetic, but also it's about the qualities that will be all possible. And what I love about textiles, which I'm going to show it, so you can still work with monomaterials. So you can have one monomaterial system, but you can still create something unique. So which is, I think it will also quite link to the discussion about sustainability, right? So today I'm going to also show some of the student projects that I supervise. So just give you like a scope of, like what is sustainability in general. And I also noticed that you already had another talk about sustainability from one of the industry colleagues. So this one is a little bit different. It's just because we are trying to avoid industrial scale processes as much as we can. So that's a very good example of Ruth Lloyd's. Now she is doing her PhD in UCL. So she synthesized some bacterial dyes for textiles. I don't know if you know, but she works with colorifics, which is like an industrial printing ink solution manufacturer, but they're just making bacterial inks and some colorants. So when we talk about sustainability, yes, it is about energy, water pollution, whether it can go to landfill, and also the consumption and fast fashion. But there are some other layers that we need to talk today, and that's why we need to say it's my research about sustainable electronics. So what is sustainable electronics? So what we know, especially in this e-textiles right now, we are trying to combine very rigid parts, very rigid components like wiring, like the batteries, or any kind of actually anything that will help you for any kind of circuitry boards elements. They are, from a textile point of view, they are rigid and they're not soft. So, and also they're not quite fit well with the realm of textiles, right? So once we just talk about textiles, we talk about drapability, we talk about comfort, we talk about, like having some kind of acceptance, like when we wear them or when we hold them. So it doesn't have to be always, or let's say when we interact with them. So the textiles itself, especially here as in the curtain space, it doesn't have to be wearable, right? So it can be quite, it also defines everything. Like what we understand, the seats that we have, like all the things that you interact. So there is this interaction, there is this human interaction with the materials. And that's the why we tackle. So where do we see the future? This is an example of an antenna structure. I'm going to describe the research behind it. We see the future of soft. So it's going to be soft. So there will be much more material-led integration. So it's not going to be just like having one component and make it work with textiles, where the textiles itself is going to be the holder of the system. So how do we see is the material itself integrated in it is also have this function of and also the capability. So where do we start? So this is a very a bit distorted version of a periodic table that like quite well. So in 2019, I was part of the organizing committee with Royal Society of Chemistry to celebrate 150 years anniversary of periodic table. And the European Chemical Society, they revised this periodic table based on the available resources left on the Earth today. So some elements you're just gonna see, apologies for the distortion in the color. So there some are like gallium, zinc, or indium, like these are like red, like shaded ones. They have like higher risk of supply in the next 100 years, which the scientists also estimate is gonna be sooner than that. So there are some icons that you see as like the mobile phone icons. They are the same metals that we use in our electronic devices. And some has some other issues like mining. There are some geographical conflicts over it. So it's not just about the earth can provide it, but there are also other, like politics behind it. And some elements in here, especially the silver and gold, these are the same metals that we use in electronic textiles a lot. So these are, like we use silver coated yarns, we use gold coated yarns. So actually it also shows us and somehow dictates the future. So our research, we are trying to use the abundant materials as much as we can. So I'm just basically leaving the behind of the space exploration, whether we can mine some new materials, but this is what we have at the moment. This is what we have, like left on Earth. So, and also imagine, like in your household, how many mobile phones or how many old iPads or how many old electronic devices that you have. So they're just basically sitting somewhere in your cupboard, right? So it's just because there are some issues, so you don't want to share your data or something, but just basically sitting it. There are quite, like there are some precious metals that we have now, for now, or at least, but in the future, they will be so precious, then we have to find some other ways to sort this waste that we even consider as like precious. So let's start. So rediscovering the resources. I think this is one of the primary motivations, whether we can use other materials for our designs. So I'm just gonna give you some kind of like a holistic approach, how you basically extract your materials. This is Marina Valentani's work, and I think she received also United Union's design award about this project. Marina started with a very problematic plant that is called Japanese knotweed, which is extremely invasive. Everyone is trying to get rid of their in their garden, and then she extracted, like different kind of dyes, fibers, foams, and then use textile techniques. It's actually creating some different kind of basketry techniques. So you may just say, okay, this is quite good, but it's how it is related with e-textiles, right? So if you just push the idea a little bit further, another student, which I love, is Emma, and she is also the material innovation designer for a Nordic company now. What she did, as her main resources, she used seaweed and used carbonation materials to replace some of the very simple electronic devices, as like is in the keyboard structure, for instance. It's just basically she replaced this pressure sensors, very carbon-based pressure sensors, which are naturally abundant materials, which is in this case the seaweed. So there are some things which is also I think is quite important. So we do not know how to deal with electronic waste, but we have no idea then electronic combined with textiles or combined with polymers or combined with other structures. So we just basically created like a monstrous structure that nobody knows. So there is no regulation. There is still some discussion in EU, but nobody knows how to deal with them now. So that's one of the things. So we are trying to basically simplify our design. So these are like very nice and very simple, like keyboard structure and some pressure sensor that these are quite handmade structures, but they were quite effective. And one of the what's it called? It's in a company that they are doing like speakers. They also use and incorporate some of their design in their production. So the textiles for communication. So the next part of the talk, I'm just going to describe two things. One is about sensing. The other one is like communication. These are some of the like the research highlights that we did over the last 6 years. So I found the communication part is a bit challenging because this is the part that the metals dominate. So if you, so this quite, I hope you can just watch it. This project started with a very simple intention, whether we can create some soft antennas. So they're going to be soft enough So they're gonna look like textiles, but also it's gonna make you feel like textiles. But also they also have some textile-like qualities, like washability. Can you wash your antenna? So this is a European Union project that that I initiated at the Royal College of Art, and I partner with Queen Mary University. They have the biggest antenna research group in the UK, and another professor in Manchester University, Professor Kocabaş, which they helped me to basically upscale their production for the graphene structures. So if you, I mean, I don't know if any of you work with communication or interested in communication, but the communication engineering is basically a field that dominates like bulky materials. So they always have like these large ground plates, you know, like for resist, you know, like resonance. And there are, so imagine like this. So you create like a variable antenna piece, but also you need like another ground plate, basically. This will be, you know, like your ground layer. So what we try to do is just basically we try to simulate and find ways to bring also the ground layer on top in a way. So it could be like a one piece, which is going to be on the surface of the textiles. These two components, you know, like which is the radiating and the ground layer is going to, you know, like work together in one. So the issue is, I think the first one is, what material are we going to use? So we are trying to avoid metals or any kind of metal inclusion. So we started to explore with using multi-layer graphene in University of Manchester. So they have such a precise control in the number of layers, which is also a bit essential because at the time we also changed the substrate. So the substrate in our case is the textiles. So the textiles can be rough and can be soft, and this can be have some, you know, like it has a texture. So it's very different than any kind of film structure. So we also need to simulate, you know, like how the response is gonna deviate, you know, like because of the crimp structures. So it was a quite hard deal at the time because the communication, you know, like engineering software is not very quite compatible with textile structures or any kind of soft structures. So we did a bit of the time in understanding the, you know, like understanding even the simulation of the result, the computational simulation of the response. So we created like different range of antenna structures. So it started with the ultra wideband communication, which is intentional. So we didn't want to use near field communication that you use in your contactless credit cards or debit cards. So it should have like a better response. Why it is critical for us, the first of all is the data privacy. And that will also, once we have a better range, that will also help us to encrypt the data. So this is the second step. So what we do is we just basically through the textiles, we decide how much, you know, like we're gonna transmit and how much information we are gonna transfer. So the standard testing in here is just we simulated the structures, measured. So we have a fairly good compatibility with the structure, but overall it's very tricky because even the simulation part is quite difficult in the computation side. But we have a very good frequency range, which allows us to give some different responses. And at the same time, once you just check the electron microscope images, you can also see how the laminated graphite antenna system is different than the other, you know, like particulate ones, which is the second printed version of it. So again, we were quite lucky to test these structures in a very industrial, you know, like standard ways in an MI chamber in Queen Mary University. So we have actually have the whole radiation pattern on the phantom body and in the testing structure. So what was the highlight of the study is actually the multi-layer graphene layer can be easily sorted and can be taken off. So that will allow us to repair the structure if it's necessary, but also it will allow us to just basically separate them into and deal with the textile waste later, and also, you know, like collect the functional piece in a separate waste. But the thing is, no one has access to, I don't know, or like it's quite limited to have a very, you know, like precise CVD is like the chemical vapor deposition, you know, like synthesis lab, right? So is it practical? That's one of the questions. Whether people can just basically do DIY their own antennas. That's one of the things. So it started. So this is a very simple explanation of a screen printing process, if you're not familiar. So to some extent, we have semi-automatic printers that we, you know, like control each ink dispersion, but it doesn't have to be. So this could be quite easy, and this could be quite handy. I think this is one of the things, whether we can formulate inks, screen printing inks, even though they're still semiconductor, they're just carbon, whether we can just create a very nice, you know, like formulation that you can work in like a home setting, which means you don't need like a high, you know, like a ventilation system or like a clean lab to synthesize it. So if you work with textiles, and you also know, so the most of the processes are quite open. So we are trying to avoid any kind of harsh chemicals, so any kind of harsh solvents. So for us, the system needs to be water-based. So this is a water-based system. And what other thing is, but if you also work with other type of carbon allotropes, could be carbon nanotube, graphene, I don't know, carbon black, they are very difficult to disperse. So you need a kind of, you either need to modify the surface, or you can use superacids. This is the carbon nanotubes case. Or what you can do, you just basically chemically modify the surface of the carbon, right? So we didn't do any of this. What we did, we just used another natural material that we called basically as a cellulose, and like a standard cellulose structure. It's just the pharmaceutical grades that we can control, you know, like I would say the polar and the apolar group of the structures. So the CNCs in this case, the cellulosic nanocrystals, they work quite efficiently, create a very good ink for us. So for the next study, I'm just going to give you all the details of the ink formulation. But we have got such a stable ink. But if you work with textiles, as I said, it's quite different than the other PIM structures. You need to be very careful. So some defects are quite unavoidable, like this, right? It's just because it comes from the crimp, you know, like it comes from the yarn itself. So it has this waviness in the structures. That's one of the parts, you know, like you need to also control and take this into effect of your simulation, right? To get a better match of the structures. So I'm just gonna show all the details in the next slides, but like that's one of the part that we also take an account of designing the ink. There are some parameters that I'm going to show you next about the rheological behavior of the inks that you can control to some extent. And that will allow, you know, like you to avoid or like keep the minimum of this kind of a defect structures. But overall, you know, like to say, so we just do like this 5 layers of structures and a very simple carbon-based carbon nanotube based things that we can get like antenna response. So these methods, actually, I work with another company called Versarien. It's also known as Cambridge Graphene. So I work with them in another industry projects, and we formulate and synthesize industrial scale screen printing inks with graphene. So they are also quite good to, I don't know if you want to buy and try, they're also quite good to create this kind of, you know, like resonating structures if you're interested in. But also these are the early studies, you know, like how we just basically control. Of course, they're industrial partners, so they also use some other surface modifiers, you know, like in their SIB, but you can also get them, you know, like with surfactant or without surfactant options. But they also, if you work with like solid structures, like some films, they also provide inkjet inks as well. So it's not just structures. So yeah, overall, this is another published study. So we are able to get like a good ultra wideband response from the screen printed carbon nanotubes antennas. And even though there's a, you know, like increase in resistivity with the washing processes, with the washing cycle, it's still, you know, like get to like an acceptable layer. But these are the studies, you know, like that we basically focus on the electrical conductivity of the structures, which with semiconductors overall it's quite limited, I would say. So, but overall, you know, like once you understand how to simulate and how to place and design the antenna structure, you can get a quite good response. So this is a study published in Nano Letters with Professor Kocabaş groups. So the communication is not just electromagnetic communications. We also created like a different electro-optical responsive and adaptive structures. So we, you know, like integrated these graphene layers into yarns. So we just basically created like a twisted structures, and it has a very good infrared response as well. So I think Ahu also gave a talk as part of this lectures. So Ahu is another Sabancı graduate. We work with her in another project that we call structural color adaptations in textiles. So the communication doesn't have to be, you know, like it doesn't have to be just electromagnetic, or so the color itself, with this kind of structures, they are cellulose nanocrystals. So you can work with the meta-stable orders to create like a response in the structures, and then we can spin some fibers, and this is part of another visual way of communication. Sensing. So I mean, if you are in the sensing field, you pretty much know you can sense everything, either through surface. So it doesn't mean that it's quite good or like the industrial scale or standard way of sensing, but I think I found sensing bits a little bit easier with textiles than the communication. It's just because how the word works. So I'm just gonna show you some one of the recent paper that we that has been accepted. It's about creating very simple and DIY voice.
No, I need to stay close
Stay close. Sorry. Yeah, I'm happy to. Sorry. Yeah, textile-based respiration sensors. So I think we learned a lot during this COVID pandemic, but I'm not gonna mention COVID at all, but it's more than that. So this is a very good map of the World Health Organizations. It's just basically showing the geographical location of how the, you know, like the world population suffer from the air pollution because of the human activities and the industrialization. So some areas you see, unfortunately, they struggle the most. And, you know, like especially in Africa and Afghanistan, India, these regions. But at the same time, these regions, the people there, they struggle the most to have like a proper healthcare system. So they don't have access to hospitals. Some they do not even, you know, like in the register. So I think this study, this is how it works, you know, like, so whether we can create like a simple respiration system that even the doctors or the medical professionals or the designers that they can create like a, you know, like an interface just for out of hospital settings, you know, like monitoring for chronic respiration and even the acute respiration response. So this is like a repetition of the same thing. So we use the same antenna, we use the same formulation of inks, but this time we have to very precisely optimize the structures. It's just because the sensing itself, we do not do the sensing just to the electrical response. So we also resolve and understand the textiles movements and the structural changes in the textiles. It will also, for us, is a very good clue and very good data for us to give us this breathing patterns of the movements. So, so this is a cellulose structure. Again, there are some ways that you can work it, but at the same time, if you're gonna work with the textile structures, then we have the just relative ratio of the carbon nanotube and cellulose nanocrystal structures. So it's not just about understanding the viscosity, whether they have like a shear thinning effect, like when you process it, which is, by the way, quite essential for any kind of processing. There are two things that are quite important. One of them, whether they are quite stable enough. So if you just leave it like off the batch, how many months you can just basically use. That's one thing. And the second one is the recovery. Whether the ink is recovered just after the printing process, which I'm going to share later. So we had a very good optimization, design of optimization for the structures, just to find the, the best or optimal concentration or the relative concentration of the structures. But this is a very good representation of the printing process. So how it works? So you just basically pour your ink, which is, in this case, is the whitish region of the structure. It's over there. The ink sits there, right? So it doesn't spread quite easily. You don't want that. So you have a fine, silk-like mesh structures. So what you have, so using a tool, so this is a very simple representation. The semi-automatic printers, they do this automatically, but you need to also pour the ink in there. So you just basically squeeze the ink, which is the second phase, right? So there's a drastic drop in the viscosity, make the structure, this dispersion, the suspension quite fluid, right? And then you just basically pull it through the geometry that you want, right? This is the second. So the ink itself needs to recover. If it spreads, then it means you can't get the tiny details of this transmission lines. So you would remember the, the previous examples of the antenna structures. There are some, defects in the structures. For us, we are trying to avoid that. And how we do that, we just basically try to understand the composition. But the body itself is also complex. So if yes, breathing is it gives you a strain level around 5 to 10. So there is some kind of a movement, but how you get your data is quite also essential. And if you're just gonna do this with your textiles, then you also need to work with different kind of sensing geometries. So they need to give you a different response, longitudinal transfers, and then, it's just basically you create a network of sensors to have a very precise and personalized kind of data sets. So that's one of the aims. So we work with this different kind of geometries. Each have some different strength in response of breathing signals. Like rain strain gauge is the simple, which is one of the easiest to resolve, and a star shape structures. And one of the things is how much layer you're gonna put, because we're also using textiles response, as a sensing parameters. So how much is too much, sort of? How many layers? You can put 10 layers, no problem. But what's gonna happen with the textiles? You have a rigid surface on top, which is it's gonna behave something separate. So it's not gonna work with textiles underneath. So it's gonna be a completely different body. So we are trying to avoid it. So it should be soft enough that will also damp and accumulate the response of the textile structures. In our case, is a knitted structure. So what is the common practice? You just basically check the IV curve, whether they have, whether it's quite enough, give you enough electrical response. But at the same time, you also need to change the monitoring of the resistance under the cyclic strain levels and understand and mapping the different strain levels response to increase of the resistivity with strain, because there's going to change. So why this is quite important for us? Because we, we normalize the data afterwards. So wherever you put your sensors, eventually they're going to be under a different kind of strain rate, cyclic strain rate. So you need to normalize it to create, your own library. So that's the processing of textiles. So if you work with the knitted structures, you can't do tensile testing. So you need to create your own structures. The common practice to understand the knitted structures is burst strength. So you just basically burst the structure and response, but it's not gonna work for us. So we have to customize our own, let's say, tensile testing structures in a way. So it's not like through the tensile testings, but it also gives us a response in longitudinal and the transverse direction. So again, these are like standalone structures. They are quite off-body. So just to see whether we have a quite repeatable breathing like patterns once we just simulate and program the actuation. And whether, which sensor in which direction, it gives you like a very good response. Just this is part of the resolving data. So we were quite lucky. So we work with medical device manufacturer based in Ankara. And they had access to this mannequin, which is like a very good simulation model in a nursing hospital. So that's another challenge. The mannequin that we found is a mother expecting a baby. So what is, that means the body have curvatures. So what we thought, initially we're just gonna work with a man model, but this is quite realistic because, the woman body itself, it has curves, it has breasts and it's different. So even to get an accurate data is kind of a challenge. So is it this position? So it's basically simulate the breathing effect and also where you place your sensor. It was a very good exercise for us to understand how effective or to what degree we can have a quite repeatable results. So you see, so we just place the sensors there. It just, even we have a response, so it needs some kind of a data transformation to match with the breathing effect, which we can also gather through the simulations on data interface. But what was the aim here is actually, we said that we are just basically aiming at low cost, affordable healthcare solutions somewhere in the village that you can, use. This is the very rough and early demonstration, whether we can transfer this breathing data to another API, and whether we can just, enable some kind of a continuous monitoring of breathing signals with a medical professional who can analyze that. So this is the second part. So this team is actually at the moment, we are just working on a bit together to create a biodegradable electronic, I would say, package or set that we can just basically share with, the people is gonna be quite a low cost, and we just basically give them the whole DIY sort of kind of instructions to create their own system. So a couple of more, actually, I'm just gonna finish it now. This is another project that I did with a Nano company. So I work with them and they have now offering, and you can also buy it, biodegradable and recyclable graphene-based textile structures like yarns. So if you are interested in, and if you, I don't know, if you are in energy applications, you may be interested in to talk to them. And it just gives you like a very good graphene-based biodegradable, it has a very good elastic ratio, which is similar to nylon, I would say. And one last bit is actually, I know we talk about sustainability. Even all this computational, efforts with the AI is not very energy efficient, which I would say for now. So we also do some research is to translate very material-like qualities for there, just understanding visually, and on those understanding sensory to create a very specific sensory materials data sets. So what we do with this, which is like one of the examples how the app itself is gonna work in another setting, is like the packaging and retail. So we developed an app that we called AI Loop. So loop is the word that we use in textiles engineering a lot. It's just a magnifying glass that you count the weft direction and the warp direction and gives you like a very clear identification of the fabric. So we do this like through an app that we called AI Loop. So you scan your fabric, like your trousers, and just basically visual recognition with the material data sets that we have in our library. It gives you all your objective properties, including the supply information, but also it gives you some sensory information. So the sensory information bit is actually critical for us for this one, because what we do through optical or like visual recognition, and also with the haptic interaction, the robots itself, let's say, they can identify the objects to a certain degree, but they can't distinguish, like one textile to another. So at the moment, the current technology, what it does, they can recognize whether it's a wood, like a marble, or as like an apple, and they can also give you, how much pressure or how much compression that they need to apply. So this kind of library, this kind of data set is going to allow the robots, or other kind of digital systems to distinguish different materials and act upon, respectively. And okay, so I think I'm just going to conclude my talk, and I'm happy to answer some questions. So this talk is more about like a provocation rather than the sharing some of the objects. But I think the time comes, came now. So we need to talk more about repairing our applied design. Whether it's it could be like a composite system, it could be like a sensing system. Whether our approach enabled to repair of the structure. So scalable is always an option, but whether it's affordable, or whether it's sustainable regarding the material sources. And which is also quite critical here. Can we just basically replace our design or material choices with some other abundant materials that we didn't, maybe we haven't considered yet? And I think we're just gonna hear more about, especially with the people in e-textiles or smart textiles. It doesn't have to be textiles, though. It's like smart materials, whether your structure is degradable or it can be repurposed for other things, which is one of the quite, I would say, like the hot topics in the design world as well. And also another thing, the materials that we can use today, whether we can also embrace another approach that is like more than human. So it's not just about designing your system for human, but what if, for afterlife of your system could be beneficial for other species? So I think the seaweed example is also a very good one. So it's not just about, disposing the structures, but what if it could be also some other nutrition, qualities, even though the humans won't, prefer to have, eat it, but it might be precious for another species. So these are the kind of, the discussion and the provocation points that I want to raise today. And I want to say thank you. Thank you for being here on Wednesday while you have many other things to do. And I will be happy to answer your questions. Thank you.
Did you check the crystallinity index and the particle size of CNC, not CNC, carbon, cellulose nanoparticles, the particle size, and also the crystallinity index, because crystallinity index is very important. So we want to produce multi-structures, or it affects the end product properties. It could be translucent or transmitted, transparent. And also, this is one of my questions. The other one is, did you try graphite fabric, because it has perfect knitting, and it is used in the standard method of boring textiles. I don't know if you have any idea. This reverse fabric has perfect knitting structure, so there is no risk to the problems you face with the normal textile. For antenna applications, you can use this kind of fabrics. I just wonder if you would try this perfect knitted fabrics to see the forms of applications. So this is the next.
So thank you for your question, but the audience couldn't hear the question. Could you repeat briefly and answer? And I have a question on the chat.
Okay. Thank you so much. So the first question about Christianity index of CNC, I think is a very good question. It's just because there is a very broad range. So I don't have the information with me, but I'm just going to check the paper after this talk if you have the time. But we use different type of cellulose nanocrystals for different applications, I would say. It's just because the one with we work with the structural color, it has a narrower range than the CNCs that we use for carbon nanotubes. But I'm happy to share the data. So they're from 2 different companies. The second question is about it's using a different characteristic. It's yes, you can use it. I haven't tried it, but the whole intention is actually to use ordinary fabrics. So just ordinary is like ordinary enough that it can be easily found, and in a way, if you can create a material system which is quite adaptable. Because we work with, so what will be the easiest option? So if you have a cellulose-based ink to use a cellulose-based structure,
yeah.
So it's just gonna, it's gonna be the easiest thing to do. But we also try different type of, textiles just to see the limitations of the design. But at the same time, whether this approach be quite practical.
I may have one more.
Yeah, sure. I will repeat them.
These are all hydrophilic-based fabrics, cellulose-based. But there are hydrophobic types, polyester, polyamide, mainly technical textiles. Do you have any work on these kind of fabrics and textiles?
Like a hydrophilic ones?
Not hydrophobic ones, but polyamide.
Yeah.
Type, for example, or polyamide.
You can easily work it. So with this one, we haven't used any binders, but in standard textile printing processes. Sorry, the question is about whether we can work with any kind of textiles and the hydrophobic and hydrophilic. So there are there's another component in standard textile printing, screen printing, that we call binders. So what they do in standard processes, they apply a binder on top. So this binder is actually it changes with the textile. So it could be like a hydrophilic, or it could be like a hydrophilic.
Two functional groups, hydrophilic and hydrophobic. One will attach to the hydrophobic, the other one is hydrophobic.
Yeah. So but that's why it's quite, I would say,
But if I
exchange
take the functional groups of graphene, for example, you can directly apply
to the air.
The cellulose to the purposes.
I think I think it will be quite good to say. So the graphene, it's precious. It's not quite easy to get. So one of the aim that we have is actually whether you can use carbon black or something. Is it about is it all about your substance in a way, or if you can understand and resolve the behavior in a kind of a short range of conductivity, whether you can work with any kind of materials, any kind of carbonized materials. This could be seaweed, or it could be another plant. It could be. I think that's one of the graphene for us. That's how we started it, because we started a very tech and focus. The communication, it's very, yeah. But I think that all the sensing parts, which I am quite fascinated, it's once you understand the structure, just the structure, even though you don't have to use like niche chemicals or like niche materials, you are able to get a response and you are able to get a property, but also, you know, like with the AI and everything, you know, like, so if we have the ability to train the data we have, then with less resources and use more the abundant materials than like a very large scale, yeah, materials. Thank you. Oh, thank you.
I need to talk to you.
Yes, I would love to. Thank you.
We have two questions on the chat. Also,
I have one more.
okay.
Okay, thank you for very inspiring talk. It's very related to what you were talking about, and you also mentioned the challenges of the fabric when you try to make a conductive line using already a not very high conductivity material. So you also mentioned the layers of accumulation on the surface, not to make a rigid body on a soft material. The question is very related to that. So is it the material property you are dealing with when you try to make these conductive lines on a very rough surface? Or is it just a matter of accumulation because you have to make this percolation to have a good conductivity and the material moves, it's a soft material, especially when you stretch a fabric. How do you tackle this challenge? How do you manage to keep the high conductivity with the movement of the fabric? Even if it doesn't move, it's just making this percolation network on a very rough surface.
I think, yeah, it's a very good question. So the question is about these transmission lines. Since they're not deposited on a very smooth surface, so there are some irregularities in the transmission, on the transmission process when we stretch and unstretch. So the first thing is, so I think the data gathering and the understanding the data part is quite critical because you need to understand to what layer the textile behaves and to what extent and after what strain levels, I would say, then you are able to see the main response of the conductive layer. So with these braiding sensors, I don't know if you just see the data, but we are basically, we don't check the strain level below 1% because that's the part that the yarn will slip. So it doesn't mean anything. So it just basically, yes, I'm just gonna get a response, but also this is quite critical. You have to understand your textiles well, and you need to understand their, you know, like their response and their, you know, directional elasticity in a way. So just to decide whether you are just basically getting the sensing from textiles or from the surface. That's also one thing, but which is quite interesting with the transmission lines. You get like very weird response, sometimes like negative resistance changes. It's just because it behaves differently. So when you have like a flat surface, you know, like when you stretch it, you just assume, oh, okay, break the, you know, like the conductivity network. So there's a different percolation and then, you know, like the electrons find a different way. But with the textiles, so it's completely different. So sometimes the textiles itself, when you stretch it, so you expect that you induce more defect in the structures, but you get transmission lines closer, so the resistivity decrease. So we saw like a decrease in resistivity. So I think that's the critical part that you need to resolve and understand, you know, like how your structure behaves. But it's also good just because you understand it's not just about the conductivity range of the material you use, but it's much more like this cumulative response and with the sensing materials. And if you just consider like along the body, then you also understand, even though you have it the same braiding effect, there are some different strain range. Then you also need it. But it's like all these things, it's like, I think this is quite data processing and AI is quite critical because these are the only ways that you can create a very personal profile, you know, like for your own personal data profile, you have had data profile. But these are all ongoing studies. But thank you so much for the question.
We have 3 questions on the chat.
I don't know how, should I just,
Can you see or
yes, please. It's just because I think it stopped here. My laptop is suffering right now. The first, yeah, do you think this carbon native CNC-based ink could be applied by inkjet printing? I tried with the graphene one, but it didn't work with the textiles. Why it didn't work? Because it took so long yeah, I mean, there are with the Versarien, again, if you're interested in, and also with the carbon nanotubes, you can reduce the composition to make it inkjet printable. That's quite possible, but with my experience with textiles, unfortunately, it didn't work. So I once left the inkjet printer open for 48 hours, and it doesn't give me it says only give me like a quite vague textile structures. It was quite difficult to control the surface.
What kind of inkjet printer?
I don't know.
Remember?
I don't remember. I have the photos.
Was it like a commercial inkjet?
It's a
printer?
commercial. It's
That
not
you
like,
buy?
yeah. It's like very standard inkjet printer
like
in an antenna lab. Yeah.
Okay.
It was like very watery kind of suspension, and we had quite hard time at the time we worked with graphene. So they had so many issues about the blockage of the, you know, like the printing head. So we sort of overcame it. It just because what we did at the time, if I'm not wrong, we also coated the surface and then play with the, you know, like the surface interaction to make the ink more spreadable on the textile surface. But overall, you know, like since the quantities, I mean, like the ink or like graphene inclusion is so minimal, it took so long. And there was no way for me, from a textile person, to say inkjet is gonna work with textiles. It's like, yes.
What thing did you use in advance?
So we printed some near-field communication, like very tiny miniature antennas for it. But it's even with them, it doesn't work. But I have some pictures on my phone. I'm happy to show it. So you can only see it's like it gives you like a brownish effect. You know, like it's yeah. It didn't work. The other question is about honor consulting, and it's about the scalability of these carbon-based materials and their integration into macro scale properties. So I would say my examples, in a way, I mean, as I said, as a design perspective, we are trying to avoid any kind of additional structures, but at the same time, I think there's also a very good debate about, you know, like the durability of the structures that we use. I know the textiles industry particularly, they dictate like at least around 50 wash cycles, but in reality, none of us wear, you know, like the same, I don't know, like wash a simple t-shirt for 50 times. So there are some, you know, like questions. So I think that's from the design perspective, I think it's quite good. Maybe it's okay to get the loose effect of some qualities. Maybe it's okay to, you know, like reapply the, I don't know, this could be like a paint, this could be something else. But yeah, I think these are the things that are quite debatable. But this is like the common practice. Oh, I have a similar name here, one of my PhD students. Hi, Sasan. We use multiple carbon nanotubes. It's just because it's actually, so there are like two things. we didn't use single wall carbon nanotubes. Again, they're not quite easily to resource. And the second of all, it's like the multi-wear carbon nanotubes that we have already in hand, and lots of people they can find it easily. But at the same time, I'm happy to share the details, but like they're not have like very high purity. I think they should be around 95. They're not like, like quite good multi-wall carbon nanotube structures for other properties. So the wash durability, we did some standard testing. So just up to, I think in the paper, up to 10 cycles. But in textile processes, like, so what we did, we like using the detergents and stuff, but any studies on the changes. So the, I don't know if you can just show the washability one. So the sensing ones, the antenna ones should be up to 5. And there's like a change in over here, but this is again set the antenna. So the other one, the sensing one, I don't remember we washed them, or maybe we washed whether it just changed the structure, but I don't think that I have the data with me. And for the durability, did you try PDMS, polydimethylsiloxane? No, we haven't used any of them. I think these are the things, like, yes, you can, there are many ways to increase the durability and the stability of the structures, but we are trying to evade any kind of additional polymeric layer on top. And also another, like additional processes that will also bring extra costs. And one of the aim of this research is whether we can create a much more sustainable, like compliance with the electronic textiles design. So actually, yeah, we intentionally avoid using some polymeric structures, including surfactants in the design. I think I answered all the questions.
Thank you for your coming, Hocam.
Thank you.
Thank you for your participation.
Thank you so much.